In this manuscript, we present Risk Euclidean Distance-Based Model Predictive Path Integral, named RESM-MPPI. Our core contribution is threefold. First, Risk Euclidean Distance Safety Metric enhancing dynamic collision assessment. Second, MPPI with risk control barrier functions ensuring safety constraints. Third, Control Obstacle Avoidance Annealed sampling adaptively balancing exploration convergence trade-offs. The overall system framework comprises sensor input, dynamic obstacle perception with trajectory prediction, and the motion planner. In the local planner, we proposed a safe trajectory planning method of RESM-MPPI. At the same time, in order to obtain better sampling trajectories, we introduced the sampling strategy of COAA. To illustrate the safety and efficiency of our proposed method, we set up 4 experimental scenarios and compared it with 2 other safety constraint methods and the MPPI sampling strategy. In static scenarios, all methods can safely reach the endpoint, and the smoothness and efficiency of the trajectory have deviations. In the scenario where the obstacle moves at a uniform speed, the safety constraints of each method begin to degrade. In the scenario where the obstacle moves at a uniform deceleration, the safety of each method has recovered to a certain extent. In the scenario where the obstacle moves at a uniform acceleration, other methods begin to seriously violate the safety constraints. All scenarios and results are shown. We set 3 indicators to evaluate the method. The minimum distance represents the effective distance between the robot and the obstacle. The arrival time represents the driving efficiency of the trajectory. The variance of the input variable represents the smoothness of the trajectory. The experimental results show that our proposed method maintains better trajectory safety and efficiency in various scenarios. To verify the real-time performance and effectiveness of our method, we built an experimental platform on the AGX Scout 2.0 differential mobile robot. Now, we conducted real-world experiments. The first scenario involved navigating through 2 pedestrians moving diagonally. The second scenario required avoiding 3 pedestrians approaching head-on. More complex dynamic scenario experiments are presented as follows. In conclusion, this paper presents a sampling-based MPC framework, incorporating the RESM-CBF safety constraint and the COAA sampling strategy. Through simulation-based comparison experiments in different scenarios, our method demonstrates superior trajectory safety and efficiency. Moreover, real-world experiments validate the real-time capability and scalability of our approach. Thanks for watching.